The morning light on the seafloor of the Western Pacific filters down in trembling waves, illuminating an expanse of fine white sand. To the casual eye, this quiet desert seems lifeless, a vast plain of dust sculpted by currents and time. But as the camera drifts closer, the monotony begins to break. A pattern emerges, faint at first, then startlingly precise. A ring of ridges and troughs radiating from a central hub, like the spokes of a sunken wheel. This is not a random formation. It is a structure of intent, a sculpture built by a creature no larger than a human hand. The architect, a male pufferfish, hovers nearby, its body pulsing with subtle undulations as it stirs the sand into order. Here, on the seabed, he practices one of the most intricate acts of animal engineering ever recorded. An ephemeral cathedral made of grains, geometry, and flow. The male puffer's work begins long before any viewer can recognize its purpose. For days, sometimes more than a week, he labors at the center of a patch of sand roughly 2 meters wide. His fins beat in short, rhythmic bursts, generating small vortices that lift particles into suspension before settling them again with surgical precision. With every pass, his body's movements imprint new ripples that reinforce those before them, an act of hydrodynamic engineering rooted in instinct. Each ridge he raises and each valley he deepens strengthens the next. Over time, these repeated fin strokes create a stable topography, a sand mandala that resists erosion from the very currents that could destroy it. The physics behind this art is elegant. As his fins sweep, they generate alternating vortices of high and low pressure. These microcurrents interact, carving lines that align with the direction of flow, a process similar to how wind sculpts dunes in a desert. Through repetition, the puffer amplifies constructive interference, the principle where synchronized waves build upon one another rather than cancel out. The result is a self-reinforcing pattern, each ridge amplifying water movement in a way that keeps its neighbors intact. The geometry is not decorative, it is functional. The circular arrangement funnels fine-grained sand and shell fragments toward the center, where drag forces are weakest. The fish has learned through millions of years of evolution to shape the flow of water itself, transforming turbulence into architecture. As the puffer moves, every part of his body serves a purpose. The broad pectoral fins act as brushes, the tail as a stabilizer, and the small undulations of his body direct sediment in graceful arcs. He rarely stops, tracing and retracing the same spirals as though rehearsing a dance choreographed by hydrodynamics. Occasionally he pauses to inspect a section, hovering motionless, eyes darting as his skin shifts from pale cream to mottled gray, a visual signal of concentration or alertness. Then, satisfied, he resumes, adjusting a ridge here, deepening a groove there. Each circle radiates with near-perfect symmetry, though no instrument guides him but his own body's rhythm and feedback from the sand. Over the following days, the structure grows more elaborate. The outer rings rise higher, catching light as they ripple outward, while the inner basin becomes smoother and more finely textured. The fish collects small shell fragments and pebbles, tiny pieces of coral and broken mollusk shells, and arranges them in the central depression. This is the stage of decoration, a phase as much about communication as construction. The arrangement of shells is not random. It enhances contrast and visual appeal, reflecting faint iridescence that shimmers in the shifting currents. From above, the mandala becomes visible even through meters of water, a target for any passing female searching for a mate. When a potential partner approaches, the male's behavior shifts subtly but decisively. He increases his swimming frequency, darting around the perimeter of the pattern to clear away stray debris. Each movement sends microbursts of sand outward, sharpening the contrast between ridges and valleys. The structure now resembles a living ripple tank, a precise interface between physics and biology. The female circles overhead, assessing not just the symmetry but the stability of the formation. The pattern must withstand both current and time, proof that the builder possesses endurance, coordination, and fitness. In evolutionary terms, the mandala is a resume written in geometry. Scientists studying these sand circles have measured their design in detail, revealing a remarkable alignment with fluid dynamic principles. The ridges channel boundary layer flow, the thin layer of water that moves close to the seabed, in ways that minimize drag across the central basin. This low drag zone creates a protected cradle for eggs once fertilization occurs. The eggs, deposited by the female and tended by the male, remain sheltered from abrasive currents and suspended silt. Even the grain size distribution within the nest follows physical logic. Fine sand accumulates where hydrodynamic pressure drops, while coarser fragments line the outer edges, reinforcing structural integrity. The entire system behaves as a self-stabilizing design, an organic blueprint that manages water, sediment, and energy simultaneously. Once mating is complete, the purpose of the artwork shifts again. The male remains to guard the eggs, hovering above them and fanning the water with gentle, calculated beats. This aerates the developing embryos, ensuring a steady supply of oxygen. His once meticulous mandala begins to erode, its perfect ridges softening under his protective movements. By the time the larvae hatch and disperse, the structure will have nearly vanished, leaving behind only faint traces, a ghost of geometry fading into the seafloor. The cycle ends where it began, the sand ready to be reshaped by the next tide or the next artist. The behavior raises questions that reach beyond aesthetics. Why has such complexity evolved in a fish so small and otherwise inconspicuous? The answer lies in sexual selection, the evolutionary engine that drives display behaviors across species. Just as a peacock's feathers or a bird of paradise's dance advertises health and vigor, the puffer's construction signals cognitive and motor skill. A male capable of maintaining perfect symmetry over days of effort demonstrates not only stamina, but spatial awareness, qualities linked to overall genetic fitness. The structure, in essence, is both message and medium. It communicates ability through action, stability through pattern, and intelligence through form. Yet this phenomenon also reflects the interplay of environmental constraint and adaptation. The sand beds where these fish live are exposed to constant wave action and sediment drift. A less precise builder would see his work erased within hours. Evolution has fine-tuned the puffer's anatomy and behavior for resilience in this specific setting. His fins are shaped for low turbulence movement, his eyes positioned for near-field depth perception, and his brain wired to respond to tactile feedback from sediment. Even his timing aligns with lunar and tidal cycles, optimizing the window of calm when currents are minimal. In this way, the puffer's craft is a product of both biology and environment, a feedback loop where the seafloor dictates form and form modifies flow. Viewed through a broader lens, this behavior invites comparisons to other forms of non-human architecture. Like the spider's web or the termite mound, the puffer's sand mandala represents a synthesis of instinct and environmental physics. Each structure, though ephemeral, embodies principles of engineering discovered independently by evolution: load distribution, aerodynamic flow, and structural symmetry. What makes the puffer's creation singular is its visible elegance, a deliberate design whose aesthetic and functional goals align perfectly. It is art without awareness of art, an emergent beauty rooted in necessity. In the final hours before the pattern's dissolution, the puffer circles its center once more, tracing the paths it has memorized through movement alone. The light shifts overhead, turning the sand surface into a canvas of moving shadows. Every ridge glows faintly in the refracted sunlight. Every trough holds a glimmer of suspended particles. From above, it looks almost like a galaxy, spiral arms radiating from a bright core, born of motion and time. Then, slowly, the current changes. A shift in tide sends a pulse of energy sweeping across the seabed. The outer ridges begin to collapse, grains slipping into the valleys. The symmetry blurs, the pattern softens, and within a day, it is gone. But the puffer has already succeeded. His message has been received, his legacy carried forward in a new generation. What remains is not the structure itself, but the story it tells, of precision born from instinct, of physics guided by biology, and of an artist whose canvas is the living sea. In a world where survival often favors simplicity, the pufferfish's mandala stands as a quiet defiance. a demonstration that complexity, too, can evolve from necessity. Beneath the waves in the shifting sand between coral and current, a tiny engineer continues to build with the language of flow, leaving behind patterns that last only as long as the water allows, and yet, in their fleeting perfection, endure far longer in the record of evolution. In the cold, green waters of the North Pacific, the light filters through layers of plankton and drifting silt, scattering into a soft haze that makes the sea itself appear alive. Beneath the surface, the silence is deceptive. A deep tremor rolls through the water column, low, rhythmic pulses that vibrate through muscle and bone. Then, from the dim distance, a shape emerges. A humpback whale, massive and deliberate, its silhouette slicing upward from the depths. It is not alone. Around it, a small team of others move in formation, their vast bodies suspended in perfect synchrony. Together, they are preparing for one of the most complex hunting maneuvers in the animal kingdom, an underwater choreography that turns air into weaponry and teamwork into engineering. The target is a school of herring, tens of thousands of individuals moving as one, a living mirror that shifts and flashes with the rhythm of the sea. Each fish is small, but together they form a resource dense enough to sustain giants. The humpback's success depends on precision. They must corral this chaotic swarm into a single column of confusion, a vortex of prey dense enough to harvest efficiently. What unfolds next is not brute force but strategy, a display of fluid dynamics mastered through experience and refined through generations of learning. It begins with a single call. The lead whale, often a female, releases a series of pulsed tonal notes that travel far through the water. The sound acts as both command and countdown. The others, positioned around her, respond by diving steeply, descending below the herring school into the darkness where pressure thickens and light fades. Down here, coordination is invisible to the eye but alive in the water's vibrations. The whales hold position in a circular pattern, like architects tracing the foundation of an unseen structure. Then, one of them exhales. A long, deliberate burst of air from its blowhole that expands into a stream of bubbles. Each bubble rises toward the surface, spinning slowly as it ascends. More whales join in, blowing in sequence, spacing their exhalations with uncanny timing. The air columns twist together into a spiral, a helix of silver spheres expanding outward, its edges shimmering like a wall of light. To a fish, these bubbles are impenetrable, a shifting barrier that looks and feels solid. The herring begin to tighten, instinctively grouping inward to avoid the apparent danger. The more the whales exhale, the stronger the illusion becomes. Soon the school is compressed into a dense cylindrical mass, a living column of prey trapped within a rising net of bubbles. This phenomenon, known as bubble net feeding, is not a random tactic. It is a precise form of engineering, the use of air and water flow to manipulate animal behavior. The whales coordinate ring diameter, spacing, and ascent speed to optimize prey density. The physics behind it are intricate. As the bubbles rise, they create vertical currents that alter local pressure fields, guiding fish upward while limiting their lateral escape routes. The diameter of the net determines how fast the bubble walls expand and how much water turbulence they generate. Narrow rings confine prey more tightly but require greater precision in timing. Wide rings capture more fish but risk lower density. Through countless hunts, the whales have learned to adjust these parameters to match the conditions: current strength, light levels, and prey response. Hydrophone recordings reveal another layer of complexity. The lead whale's call is not just a rallying signal, it is a metronome that synchronizes movement. Each note marks a phase of the ascent, the moment to tighten the circle, the cue to rise, the signal to exhale again. The entire group follows this acoustic blueprint with astonishing coordination. Drone footage taken from above shows the pattern forming like a rotating galaxy, each whale's path precise and deliberate. The final spiral closes just as the whales begin their ascent, driving the trapped fish upward toward the light. At the surface, the sea explodes. A dozen gaping mouths surge through the confined column of fish, each whale engulfing tens of thousands of prey in a single lunge. The sound is thunder underwater, the rush of displaced water, the crackle of collapsing bubbles, the muted thud of closing jaws. Then, silence again. The whales sink back beneath the surface, regroup, and begin anew. Each feeding cycle lasts only a few minutes but can sustain an entire pod for hours. What makes this behavior even more remarkable is its cultural dimension. Bubble net feeding is not instinctive, it is learned. Not all humpback populations use this method, and even among those that do, the technique varies by region and group. Off Alaska, whales form large cooperative teams that spiral upward in near-perfect helices, while populations in the southern hemisphere often use half rings or paired bubble walls. Some groups have been recorded adding vertical columns of bubbles, pillars instead of rings, to manipulate schooling fish in tighter spaces. These variations spread not through genetics but through imitation. When a juvenile joins an experienced group, it learns by observation, gradually mastering timing, positioning, and call sequence. Over time, these refinements accumulate, creating what scientists describe as cultural evolution, the transmission of behavioral innovations across generations. This cultural learning extends beyond hunting mechanics to role specialization. Not every whale in the group performs the same task. One acts as the caller, maintaining acoustic cohesion. Others serve as ring builders, exhaling at precise depths and intervals. Another may function as the closer, releasing a final burst of air that seals the column. Such division of labor implies a level of cognitive organization rare among non-human animals. It demands memory, coordination, and perhaps even anticipation, an understanding of what each partner will do next based on shared experience. The environmental consequences of this cooperation ripple far beyond the hunt. By targeting dense herring schools, the whales help regulate population structure, influencing the behavior of seabirds, seals, and even smaller predators that depend on the same prey. The disoriented fish driven to the surface attract flocks of gulls and shearwaters, while sea lions often capitalize on the chaos, darting through the bubbles to snatch stragglers. In this way, a single whale pod becomes the catalyst for an entire ecological event, a mobile feast that links species across multiple trophic levels. The precision of bubble net geometry also highlights the humpback's sensitivity to hydrodynamics. Studies using underwater lasers and acoustic sensors show that whales fine-tune their exhalation pressure to control bubble size and rise speed. Larger bubbles ascend faster, but are less cohesive, while smaller bubbles persist longer, creating a more stable barrier. The whales strike a balance by modulating exhalation force with remarkable subtlety. This control is facilitated by specialized musculature surrounding the blowhole and by lungs capable of rapid pressure regulation, adaptations that evolved primarily for diving but now serve a secondary purpose as tools of manipulation. The coordination required for this behavior pushes the boundaries of what we understand about non-human communication. Each whale must track the position and velocity of others through sound alone, interpreting low-frequency cues that travel over distances of hundreds of meters. The precision with which they maintain spacing suggests not only acute hearing, but real-time processing of auditory information. Researchers have compared this to a form of sonar-based situational awareness, a sensory web that binds the group together through the physics of sound. When the hunt ends and the pod disperses, the sea returns to quiet. The circular patterns of bubbles dissipate, rising to the surface and bursting one by one. But even in absence, the structure remains visible in the mind's eye, an invisible architecture built of collaboration and mastery. The whales sink into deeper layers, their calls fading into the distance, a reminder that these are creatures who have learned to turn air and sound into tools of survival. For all its beauty, the bubble net is a fragile art. Changes in ocean temperature, prey migration, and noise pollution threaten its continuity. The herring schools that once gathered predictably are shifting in range, and human activity increasingly masks the low-frequency calls the whales depend on for coordination. Yet the persistence of this technique, passed from whale to whale, refined with each season, suggests resilience. Culture, even in the ocean's vastness, acts as memory. It carries solutions through time, adapting them to new challenges. As twilight filters down through the water, the humpbacks rise once more for a final feeding. The lead whale begins the first note, a long, rising tone that ripples through the sea. The others respond, falling into position, invisible but connected through sound. Again, the bubbles bloom, spiraling upward in luminous chains, each sphere catching the last light of the day. From above, the ocean glows faintly, the geometry of survival unfolding one more time. And in that fleeting structure of air and motion, one can glimpse something extraordinary. Intelligence made visible, cooperation rendered in physics, and a song that shapes the sea itself. The tide is slack, and the water holds its breath. In the faint half-light before dawn, the shallows appear motionless, an unbroken mirror of glass-green water stretched over fine, pale sand. Yet below this calm surface, the seabed is restless. Grains shift, tiny eddies curl and collapse, and then, from the dim distance, a dark shape glides into view. A stingray, wide and weightless, moves as though drawn by invisible threads, its pectoral fins undulating in a slow, hypnotic rhythm. Each motion stirs the boundary between water and sand, blurring the sea floor into a haze of suspended particles. Within moments, the animal vanishes beneath its own storm of sediment. Only the faint outline of its body remains visible, like the ghost of motion carved into the seabed. Stingrays are architects of disturbance. Where most marine life seeks stability, they specialize in controlled chaos. Using powerful pulses of their disc-shaped fins, they generate localized pressure waves that liquefy the upper layer of sediment, a process marine biologists describe as fluidization. The effect is mechanical but elegant. With each downward beat, the ray's body compresses the sand, forcing water through the grains until they lose cohesion and begin to flow like liquid. As the substrate softens, the stingray buries deeper, flexing its fins to direct currents beneath its body. The sand begins to swirl outward, forming a ring of turbulence that expands in slow motion. Within minutes, the flat seafloor has transformed into a crater, steep-walled, symmetrical, and several body lengths wide. This excavation is not idle behavior. It is foraging in motion. Hidden beneath the sand are the stingray's targets, buried mollusks, small crustaceans, polychaete worms, and other invertebrates that spend their lives concealed from the light. The stingray's body is tuned to detect them. Along its snout and ventral surface lie arrays of electroreceptors known as ampullae of Lorenzini, gel-filled canals that can sense the faint bioelectric fields emitted by living tissue. Even a muscle twitch or a heartbeat beneath the sediment generates a detectable signal. Guided by this map of invisible currents, the ray positions itself precisely above its prey, then delivers the coup de grace, a series of rapid fin beats that blow away the sand like dust in a storm. The physical mechanics of this act are extraordinary. Water jets along the stingray's underside at speeds that can exceed 1 meter per second, channeled by the coordinated motion of the fins and amplified by the animal's flattened shape. Each pulse displaces thousands of grains of sand, scouring the substrate until the prey is exposed. Once revealed, the stingray uses its mouth, positioned on the underside of its body, to suck in both prey and sediment. Inside, a pair of crushing dental plates grind shells and exoskeletons with ease. The sand, now useless, is expelled in a puff through the gills, leaving behind a clearer pocket in the center of the crater. But the impact of this behavior extends beyond feeding. The stingray's excavation transforms the physical landscape of the sea floor. Each crater becomes a miniature ecosystem, a temporary oasis in an otherwise uniform expanse. When the ray departs, the disturbed sediment begins to resettle, but its structure has changed. Nutrients once locked deep below are brought to the surface. Oxygen-rich water infiltrates lower layers of sand, stimulating microbial activity. Within hours, opportunistic scavengers arrive. Small shrimps and crabs pick through leftover detritus, while gobies and blennies dart along the edges, exploiting the new topography for shelter. By the following day, worms and filter feeders begin to colonize the exposed substrate, burrowing into the freshly loosened soil. Marine ecologists refer to these events as bioturbation, biological disturbance that alters sediment chemistry and community structure. In the case of stingrays, this process occurs on a scale large enough to reshape entire habitats. A single individual may excavate dozens of pits in one night, leaving behind a patchwork of craters that persist for days before currents smooth them away. Studies using drone and sonar mapping have revealed that in regions with high stingray densities, such as tropical lagoons and continental shelf flats, these feeding scars can cover up to 30% of the benthic surface. Far from being destructive, this patterning increases biodiversity, creating mosaics of microhabitats that support a broader range of species than uniform sand plains ever could. As darkness deepens, the stingray's world comes alive. The cooler temperatures and diminished light offer cover from predators and reduce visual detection by prey. Many species, including southern stingrays and blue-spotted rays, time their foraging to coincide with these nocturnal windows. Viewed through infrared or low-light cameras, the scene unfolds like a slow-motion ballet. A stingray hovers above the seabed, the muscles of its fins rippling like wind over fabric. Each pulse sends a plume of sediment billowing upward, obscuring the creature entirely. Then, as the cloud disperses, a crater remains. A perfect circle bordered by raised ridges, its interior marked by the faint trace of fin imprints. The animal drifts away, only to repeat the process a few meters farther on, leaving behind a trail of shallow depressions like footprints across the ocean floor. By midnight, the lagoon floor resembles a lunar landscape. Dozens of pits glisten faintly under the filtered moonlight, each one a testament to the night's work.
Into these hollows creep the secondary wave of life. Hermit crabs scavenging for scraps, brittle stars unfurling their arms to feed on suspended detritus, and small juvenile fish seeking refuge from open water predators. Even the chemical signature of the water changes within these depressions. Elevated concentrations of ammonium and phosphate, liberated from deeper sediments, attract planktonic organisms, which in turn lure filter feeders and small predators. What began as a single act of foraging now sustains an entire chain of ecological interactions. The process continues until dawn, when the first streaks of sunlight penetrate the water column. As visibility returns, the stingrays retreat to deeper channels or bury themselves under thin layers of sand to rest. The feeding grounds fall silent again, but their transformation lingers. Over the next few hours, the newly formed pits begin to fill with fine silt carried by the tide. Some are quickly erased by wave action. Others persist longer, reinforced by biological activity. Small fish schools hover over them, taking advantage of the nutrient-rich microcurrents rising from decomposing organic matter within. Worms reburrow into the soft substrate, and the microbial communities beneath the surface flourish. The crater has become not just a feeding site, but a functioning ecological niche. Researchers studying these dynamics often describe stingrays as ecosystem engineers. Like beavers building dams or elephants knocking down trees, they alter their environment in ways that affect countless other species. The steep walls of their pits create vertical relief on otherwise flat terrain, offering refuge for species vulnerable to predation. The organic material unearthed by their feeding increases nutrient turnover, enhancing productivity across the benthos. Even after the crater collapses, its legacy persists. Subtle differences in sediment composition and oxygenation remain detectable for weeks. In this sense, the stingray's hunt is also a form of habitat creation, an ongoing cycle of destruction and renewal that fuels the vitality of coastal ecosystems. One might imagine that such behavior evolved purely for individual gain, yet evolution rarely acts in isolation. Over time, these feeding habits have co-evolved with the prey and environments they shape. Some burrowing invertebrates, for instance, now use stingray craters as primary habitats, timing their reproductive cycles to coincide with the ray's nightly disturbances. Fish larvae settle preferentially in these depressions, where reduced currents and elevated nutrients create ideal nursery conditions. Even certain predators, like moray eels and small reef sharks, patrol the perimeters of active foraging sites, capitalizing on prey displaced by the ray's excavation. By the time the next night descends, the ecosystem has reset. The once smooth seabed, enriched and restructured, awaits the return of its engineers.
The tide changes, drawing in cooler water from offshore.
Out of the darkness, the first shadow appears, the unmistakable silhouette of a ray, wings outstretched, gliding low against the sand.
With a subtle flex, it begins again, the same timeless cycle of motion and transformation. Sand lifts, swirls, and resettles. Grains cascade down the crater walls like miniature avalanches, and in that quiet, suspended moment, the ocean rewrites itself grain by grain. To the untrained eye, a stingray's pit may seem transient, a blemish soon erased by tide and time. But within these temporary structures lies a profound truth of marine life, that survival and creation are not opposites, but partners. Each pulse of the stingray's fins is both an act of consumption and of construction, shaping the physical and biological landscape of the sea. As dawn breaks once more, the camera pulls back to reveal the broader pattern. Hundreds of craters scattered across the lagoon floor, each a microcosm of life, each a reminder that even in the quietest corners of the ocean, the architects of change never sleep. In the shallows of the Indo-Pacific Reef, where sunlight fractures into ribbons of turquoise and gold, the water hums with a low, constant rhythm, the pulse of coral life at work. Every crevice is alive with motion. Cleaner wrasses dart among parrotfish, anemone fish hover in the swaying tentacles of their hosts, and clouds of chromis glitter in the open water. The reef seems serene, a delicate city built by colonies of tiny polyps, each depositing limestone over generations to form the vast, ornate architecture of the sea. Yet within this city moves a giant whose presence is felt long before it is seen. A slow, deliberate shadow gliding over the coral heads, the unmistakable bulk of a Napoleon wrasse. The Napoleon wrasse, also called the humphead wrasse, is a titan among reef fish. Males can grow longer than 2 meters and weigh as much as a full-grown human. Their thick, blue-green bodies carry the weight of authority in these waters. The broad forehead, from which the fish earns its name, rises like a sculpted dome, and the lips, thick and expressive, are as dexterous as the fingers of a primate. For such a large creature, it moves with surprising grace. But when it hunts, this calm facade gives way to sudden, brute precision. The Napoleon wrasse is one of the few fish capable of breaking coral itself, a behavior that makes it both a destroyer and, paradoxically, a gardener of the reef. A single strike is enough to change the landscape. The wrasse approaches a coral outcrop with slow surveying motions, its small eyes scanning for movement within. It is searching for one of its preferred prey, a burrowed mollusk, a sea urchin, or a crustacean sealed in the maze of coral branches. These creatures rely on hard shelter for survival, and most predators lack the means to breach it. The wrasse, however, is equipped with one of the most formidable feeding tools in the marine world, fused jaw plates powerful enough to shatter limestone. With a rapid thrust of its head, it delivers a bite that echoes like a muffled crack through the reef. Fragments of coral tumble to the sand below as the fish grips its prey and crushes it to pulp with rhythmic snaps of its jaws. This destructive force is not mindless violence, it is precision feeding evolved over millennia. Inside the wrasse's mouth, the front teeth grip and pry, while a second set, pharyngeal jaws located in the throat, act like a mortar and pestle, grinding shells and spines to fine grit. Few organisms can digest calcium carbonate, yet the wrasse has evolved enzymes and gut microbes capable of processing fragments of coral and shell, extracting nutrients where others cannot. The result of its foraging is unmistakable, patches of broken coral littered with rubble, as if a storm had passed through. At first glance, these demolition sites look like scars, bare patches amid the lush coral gardens, chaotic and raw. But what appears as destruction on a small scale is the beginning of renewal on a larger one. Coral reefs, like forests, depend on cycles of disturbance to regenerate. When the wrasse smashes coral structures, it exposes the underlying limestone substrate and releases trapped sediments, clearing space for new growth. The broken fragments serve as colonizing material for fast-growing coral species, particularly branching types like acropora, which thrive on open, sunlit surfaces. Algae soon coat the rubble, attracting grazing herbivores, surgeonfish, rabbitfish and parrotfish, which keep algal growth in check while fertilizing the substrate through their waste. Within weeks, the once barren crater becomes a patch of productivity. Marine ecologists studying these micro-disturbance zones have come to view the Napoleon wrasse not as a vandal, but as an ecological catalyst. By selectively disturbing portions of the reef, it prevents coral communities from becoming dominated by a few slow-growing, space-occupying species. The result is increased heterogeneity, a patchwork mosaic of different coral ages and forms that supports greater biodiversity. This process mirrors the concept of intermediate disturbance in terrestrial ecosystems, where periodic events like fires or floods maintain ecological balance by resetting succession. In the reef, the wrasse plays a similar role, its foraging acting as both pruning and renewal. The effects unfold slowly, visible only when one observes the same patch through time. In the first few weeks after a feeding event, fine sediment settles into the cracks and the small grazers arrive, picking through the detritus for organic scraps. Tiny gobies take up residence among the debris, using it as camouflage against predators. By the third month, algae cover most of the exposed substrate, forming a green carpet that stabilizes the loose coral pieces. Juvenile corals begin to appear, millimeter-sized colonies of Pocillopora and Montipora clinging to the cleaned rock, their polyps extending into the current to capture drifting plankton. By the end of the year, the site has transformed again. Soft corals sway in the flow, small sponges anchor to the ridges, and the pit itself becomes a hub for crustaceans, worms, and grazing fish. Each rubble field, as researchers call it, becomes a temporary microhabitat that passes through stages of succession. The process is not linear. Storms, temperature fluctuations, and other foraging events continually reset portions of the patchwork, creating an ever-changing mosaic of life. Over larger scales, decades and beyond, these dynamics help maintain the resilience of coral reefs. In regions where apex predators and large foragers like the Napoleon wrasse have been removed through overfishing, reefs often become more uniform, dominated by a few hardy but less productive coral species. Without natural disturbances to break and renew them, these systems lose both complexity and adaptive potential. The wrasse's ecological role extends beyond coral demolition. Its diet includes toxic species like crown-of-thorns starfish, whose population explosions can devastate coral reefs across the Pacific. Most predators avoid the starfish's venomous spines, but the Napoleon wrasse uses its thick lips and crushing bite to flip and consume them safely, reducing outbreaks that could otherwise smother vast reef sections. In this sense, the wrasse serves as both gardener and guardian, one of the few natural checks on a species capable of ecological catastrophe. Watching a reef through the changing seasons reveals the rhythm of this cycle. In early summer, as water temperatures rise, the wrasse patrols more actively, exploiting the abundance of invertebrate prey. Its feeding events are frequent, scattering debris that drifts with the tide. By autumn, algae flourish across the disturbed areas, stabilizing sediment and attracting herbivorous fish in dense schools. Winter brings storms that redistribute sand and rubble, while cold upwellings slow coral growth but enrich the water with nutrients. When spring returns, coral larvae spawned from nearby colonies settle onto the refreshed substrate, the first generation of new builders reclaiming the ground once leveled by the wrasse's jaws. Over time, the reef's surface becomes a living record of disturbance and renewal, each patch a layer in the story of resilience. The Napoleon wrasse's presence, however, is increasingly rare. Its large size and slow reproductive rate make it vulnerable to overfishing, and it is heavily targeted in the live reef fish trade, where adults fetch high market prices. In many regions, populations have plummeted, leaving entire reefs without their silent engineers. The ecological consequences are subtle but profound. Without the wrasse's periodic disturbance, coral cover becomes more homogeneous. The fast-growing opportunistic species dominate, but without subsequent renewal, they age and die in unison, leaving the reef susceptible to bleaching and disease. The system loses its patchwork diversity, its natural pattern of scars and recovery that once made it strong. To fully understand the significance of the Napoleon wrasse, one must look not at a single moment, but across years, watching as cause and effect ripple outward. Each bite that shatters coral vaults sets in motion a cascade of responses, physical, biological, and chemical, that reshape the reef's architecture. Where the fish once struck, new life takes hold, faster and more varied than before. The paradox is complete: destruction as creation, loss as renewal. The reef survives not despite disturbance, but because of it. In the final light of day, the water glows with the colors of the reef, pinks, oranges, and violets shimmering through the ripples. The Napoleon wrasse glides slowly across the landscape it helped shape, passing over mounds of coral that will outlive it by centuries. Around its path, the rubble patches shimmer with movement. Schools of juvenile fish weave through soft corals that sprouted from broken skeletons, while sea cucumbers filter the sand for organic debris. Each fragment, each grain, each newly anchored coral polyp is part of the same continuum, a living cycle powered by the pulse of destruction and rebirth. The reef, at first glance so fragile, reveals its true nature as a dynamic, ever-evolving engine of life. And in the quiet beneath the waves, the Napoleon wrasse continues its ancient work, breaking to renew, feeding to create, sculpting balance from the tension between force and fragility. Beneath the surface of the tropical shallows, the reef stretches outward like an ancient fortress, its walls built from generations of coral architects, each layer a record of life and death compressed into stone. But here, on the sunlit slopes where waves break and currents whisper through cracks, another kind of builder is at work. They move slowly, almost invisibly, their spines glinting in the blue light. Sea urchins, millions of them, crawl across the reef in patient armies, their bodies no larger than a fist, yet armed with the tools to carve an empire into sand. The soundscape of this world is not silence but rasp. If one could shrink to the size of a hermit crab and place an ear to the limestone, the reef would hum with the faint grinding of thousands of urchin mouths at work. Each animal carries beneath its spherical shell a remarkable feeding machine. Aristotle's lantern, named centuries ago when early naturalists first dissected its intricate geometry. It is a complex assembly of 5 calcareous teeth, arranged in a circle and capable of protruding, retracting, and rotating in unison. The mechanism is so precise that it can scrape algae from solid rock or bore deep into coral skeletons. Every bite removes microscopic layers of calcium carbonate, the same material that forms the reef itself. Over time, the collective feeding of these creatures reduces coral strongholds to fine sediment, the raw ingredient of tropical beaches. This process, known as bioerosion, is one of the great unseen forces shaping the ocean's landscape. It may seem paradoxical that the very animals destroying coral are also the architects of islands, but nature thrives on contradiction. The powdery white sands that draw tourists to the Maldives, the Bahamas, and countless Pacific atolls exist because of this daily work. Each grain represents the slow transformation of reef into sediment, ground down by the rasping teeth of urchins, parrotfish, and other grazers. Of these, the sea urchin is the most persistent, a tireless sculptor whose appetite never rests. In some regions, a single individual can erode several kilograms of carbonate per year. Multiply that by millions, and entire shorelines are shaped, extended, and maintained through their labor. The urchin's body plan is a marvel of evolutionary economy. Its test, the hard shell that forms the globe of its body, is built from interlocking plates of calcium carbonate arranged in a near-perfect sphere. Each plate fits precisely with its neighbors, forming a structure both rigid and light. From this shell emerge hundreds of spines, movable through a network of tiny ball and socket joints. These spines serve multiple functions: armor against predators, levers for locomotion, and tools for digging into rock. Beneath them, the urchin's tube feet, soft, flexible extensions of its water-vascular system, grip surfaces with hydraulic precision, allowing it to cling to sheer walls or crawl across shifting sand. Every movement is slow but calculated, driven by coordinated pressure changes that give it surprising agility for an animal with no brain and no eyes in the human sense. Instead, The sea urchin's entire body acts as a sensory array. Light-sensitive cells distributed across its surface allow it to detect shadows and patterns, functioning as a primitive distributed eye. When a predator's silhouette passes overhead, a wrasse or triggerfish perhaps, the urchin responds immediately, retracting its spines and tightening its grip. This whole-body awareness is part of what makes the species so resilient. It does not rely on centralized decision-making, but on networked feedback. A living example of decentralized intelligence evolved long before the term existed. On a healthy reef, urchins play a vital role in maintaining balance. They graze constantly on the fine film of algae that coats coral surfaces, preventing the algae from smothering living colonies. Without them, fast-growing algae can outcompete corals for space and light, turning vibrant reefs into mat-covered plains. In this state of equilibrium, the urchins are gardeners, trimming the reef surface to allow coral recruits to settle and grow. The result is a mosaic: patches of live coral, areas of crustose algae, and zones of bare substrate, each supporting different species of fish and invertebrates. Biodiversity peaks under such moderate grazing pressure as competition is kept in check but productivity remains high. Yet when that balance tips, the consequences can be catastrophic. If predators like sea otters, lobsters, or triggerfish are removed through overfishing, urchin populations explode. What begins as maintenance becomes overconsumption. In temperate waters, this dynamic gives rise to what ecologists call urchin barrens, vast, desolate landscapes where kelp forests once thrived. Every blade of kelp is consumed, leaving only encrusted rock and drifting detritus. The loss cascades upward through the food web. Fish that relied on the kelp canopy for shelter vanish, crustaceans lose their hiding places, and even seabirds suffer as the productivity of the ecosystem collapses. Similar processes unfold in tropical reefs, though the outcome differs in texture rather than scale. When unchecked, urchins strip away algae and weaken coral structures faster than they can regenerate, reducing complex architecture to rubble. Paradoxically, the opposite extreme, total absence of urchins, can be just as damaging. In parts of the Caribbean, the mass die-off of the long-spined urchin Diadema antillarum in the 1980s led to an explosion of algae that smothered coral reefs for decades. Coral recruitment plummeted, and entire ecosystems shifted toward algal dominance. The lesson, clear and sobering, is that the ocean's architects require architects of their own, grazers that moderate the system through their daily routines. To understand the global impact of urchins, scientists track what they call the carbonate budget, the balance between production and erosion of calcium carbonate in a reef system. Coral and other calcifying organisms add to the budget, building structure upward. Grazers and boring organisms subtract from it, wearing it down. When the budget remains positive, the reef grows and can keep pace with rising sea levels. When it turns negative, the structure collapses, eroding faster than it can rebuild. Sea urchins are central to this equation, their influence measurable not in individual actions but in collective weight. In some Pacific atolls, they contribute nearly half of the total bioerosion. The sand they produce drifts with the tides, filling lagoons and washing ashore, forming beaches that in turn protect coastal vegetation and human settlements. But this constructive outcome relies on balance. Too much erosion, and the reef loses height and wave protection. Too little, and sediment supply diminishes, starving beaches of replenishment. Understanding how these dynamics shift with climate change, ocean acidification, and fishing pressure is now a key frontier in marine science. Rising acidity, for example, weakens both coral skeletons and urchin tests, potentially altering the pace of erosion in unpredictable ways. Some studies suggest that urchins might even accelerate their feeding as corals soften, compounding the damage. Others propose that in certain conditions, their grazing could prevent algae from overwhelming stressed reefs, offering a form of resilience. The truth likely lies between, a system of feedbacks as complex and fluid as the ocean itself. At dusk, the reef changes character. Daytime fish retreat into crevices and nocturnal species emerge. The water cools slightly, and the faint blue of the surface gives way to deep indigo. Now the sea urchins become truly active. Under the dim light, hundreds of them rise from their daytime refuges, moving out onto open rock faces in search of food. Their spines sway gently in the current, like fields of grass in a breeze. Tiny shrimp and brittle stars weave between them, using the urchins as mobile shelter. It is a slow-motion migration, a nightly ritual that sculpts the reef grain by grain. By dawn, the work is done. Fine trails of dust mark their feeding paths, leading toward small depressions where coral skeletons have been rasped to powder. The current picks up these grains, carrying them away to settle in deeper channels or drift toward shore. There, waves will grind and polish them further, transforming them into the sand that underpins entire ecosystems of their own: seagrass beds, mangrove roots, turtle nesting beaches. The connection between reef and coast, between the unseen rasping of spines and the familiar crunch of sand beneath human feet, becomes unmistakable. From destruction comes construction, from erosion comes renewal. The sea urchin, a creature few notice and fewer understand, is both sculptor and servant of the sea. Its slow grazing writes the story of coastlines, converting hard reef into soft horizon. Every beach begins here, in the patient turning of stone into dust beneath the spines of these ancient grazers. And in that endless cycle, from coral to sand to coral again, lies one of the ocean's most profound truths: that the boundaries between creation and decay are not opposites but partners in the same rhythm that keeps the planet alive. The seafloor here is neither pristine coral nor endless sand. It is something in between, an uneasy mosaic of shell fragments, broken crab claws, and the occasional glint of glass. A soft current drifts across the landscape, stirring fine sediment into faint suspended veils. Among the debris, something stirs, a sudden liquid ripple as an octopus slips from the shadows of its den. Its body changes color with every movement, pigments flashing through waves of pattern that mimic the shifting light above. To the untrained eye, it appears like an illusion taking form, a living mirage built of muscle and mind. This is the octopus's home, part shelter, part armory, part kitchen midden. Around its entrance, scattered remains of past meals form a halo of calcium white against the darker sand. Broken clam shells, scallop valves, crab carapaces, and fish bones lie arranged not by design but by habit, each piece discarded after consumption, accumulating over time. Yet these remains do more than tell the story of an animal's diet. They transform the seafloor itself. As middens grow, they trap fragments of drift material, bits of coral rubble, seagrass stems, shards of glass bottles, even lost metal pull tabs. These heaps of detritus alter the local flow of water, creating small eddies that redistribute sediment and nutrients. What began as a feeding ground becomes an engineered habitat, an unintentional structure that reshapes its surroundings. The den lies at the heart of this transformation. For an octopus, home is not merely a refuge, it is a functional workshop. The den is excavated with surprising precision. Using its 8 flexible arms, the animal removes stones and rubble from within, carrying each piece several body lengths away to clear space. The arms are not identical in skill. Some specialize in manipulation, while others provide stability. Experiments have shown that octopuses demonstrate lateralized behavior, roughly the equivalent of left or right-handedness in humans, favoring certain arms for tasks requiring fine control. Once the cavity is hollowed to the desired depth, the entrance is reinforced with larger stones or shell plates. These are not random placements. The octopus tests each piece, rotating it with its suckers until the fit is exact. The resulting structure can withstand both predators and the shifting forces of current and tide. Inside, the octopus arranges its lair with quiet economy. The floor is smoothed, the ceiling lined with sand to minimize glare from above. The animal's body is soft enough to conform to the space, reducing visible outlines when viewed from the entrance. At rest, its skin adopts muted tones of the surrounding sediment, broken by faint, irregular mottling, camouflage perfected over millions of years. It can match the texture as well as the color of its environment, thanks to chromatophores, pigment sacs, layered with papillae that raise or flatten to change the skin's physical structure. Each adjustment is instantaneous, directed not by conscious thought, but by a neural network that distributes control throughout its body. In an octopus, the majority of neurons reside in its arms rather than its brain, giving each limb a degree of autonomy that borders on independent intelligence. When the octopus feeds, its den becomes a processing station. A crab caught in the open is carried back alive, its struggles subdued by precise injections of venom from the octopus's beak. The prey is methodically dismantled, soft tissues consumed and exoskeletons discarded. Over weeks, months and seasons, the accumulation of these leftovers transforms the surrounding terrain into a ring of debris. This midden, though incidental, has ecological consequences far beyond the den. It provides shelter for small opportunists, shrimp, amphipods and juvenile fish that slip between shells to avoid predators. Worms colonize the inner crevices, feeding on organic residue. Microbial communities bloom, releasing nutrients that enrich the surrounding sediment. A single octopus, by virtue of its feeding habits, can alter the biodiversity of several square meters of seafloor. In certain coastal regions, the density of these layers reaches remarkable levels. Off eastern Australia, scientists discovered a site dubbed Octopolis, an underwater settlement where dozens of octopuses live in close proximity, their dens built amid a field of shells, metal scraps and human debris. The area, roughly the size of a tennis court, has become a self-reinforcing habitat. Each individual contributes to the growing accumulation of material, and new arrivals use these existing structures as foundations for their own dens. Over time, the collective activity transforms an otherwise featureless seabed into a patchwork reef, a form of accidental urban planning driven not by cooperation but by shared utility. The octopuses do not build together intentionally, yet their overlapping behaviors generate a structure that functions much like a communal ecosystem. In Octopolis, social interactions are both rare and intense. Octopuses are solitary by nature, avoiding direct contact except for mating or territorial disputes. But in this artificial reef, proximity forces confrontation. Males defend dens aggressively, spreading their arms and darkening their skin in threat displays that ripple with chromatophore pulses. Females, typically smaller, navigate the contested terrain with caution, their movements calculated to avoid triggering aggression. Predators, such as moray eels and wobbegong sharks, circle the perimeter, drawn by the concentration of prey. Yet paradoxically, the very structures that attract them also provide cover. The layered rubble and shells deflect water flow, breaking up the silhouettes of hunting fish and giving the octopuses critical seconds to retreat. The architecture of Octopolis becomes both shield and stage, a physical embodiment of the tension between creation and destruction that defines marine life. To test how these structures influence ecology, researchers deploy flow sensors and particle tracers around active dens. The data reveal a striking effect. Water slows near the shell piles, reducing sediment resuspension and creating microzones of stability. These calm pockets allow detritus to accumulate, supporting benthic invertebrates that in turn attract scavengers. Crabs, brittle stars and small fish forage among the remains, while octopus predators, like conger eels, find their approach hindered by the complex terrain. The middens act as both barrier and attractor, shaping the distribution of life in ways similar to natural reefs. In essence, the octopus, without intention or collaboration, becomes an ecosystem engineer. From an evolutionary standpoint, this behavior reflects a profound adaptability. Octopuses are generalists in body, but specialists in behavior, capable of manipulating their environment through learned experience. In laboratory settings, they recognize objects, solve puzzles, and even use tools. Field observations confirm that wild individuals collect coconut shells or clam halves to create portable shelters, behavior once thought exclusive to vertebrates. In areas of high human impact, they incorporate glass bottles, jars, and metal cans into their dens. The materials differ, but the principle remains constant: the transformation of the environment to meet immediate survival needs. Over time, these adaptations accumulate, demonstrating a form of behavioral flexibility that allows octopuses to thrive in habitats ranging from coral reefs to muddy estuaries. Their ability to repurpose human waste underscores an unsettling truth about the Anthropocene ocean. The debris littering the seafloor, bottles, plastic cups, and rusted machinery, has become part of the natural order. Octopuses, ever pragmatic, exploit these materials as readily as shells or stones. A glass bottle offers smooth walls that deter predators. A piece of rebar serves as an anchor for camouflage. In Octopolis and other similar sites, what began as pollution has evolved into architecture. The octopus does not discern between natural and artificial. It uses what the world provides, rewriting the rules of adaptation in real time. Yet these urban reefs remain fragile. Octopuses have short lifespans, often only a year or two, and their dens are temporary by design. When a resident dies or moves on, the structure may collapse or be overtaken by scavengers. Still, the influence persists. The shell rings endure for years, accumulating layer upon layer as successive occupants reuse and expand them. Over centuries, such patterns could contribute to sedimentary records, not unlike fossil reefs, markers of intelligence and habit left in the geological archive. At dusk, the octopus returns from its hunt. Its body, sleek and ghostly, slips once more into the sheltering dark of its den. Around the entrance, the midden gleams faintly under the fading light, an unintentional monument to both survival and transformation. Small shrimp sift through the fragments, feeding on what remains. A brittle star curls its arms around a bottle lip, filtering particles from the current. The water moves softly, slowed by the architecture of discarded life. Here, intelligence leaves no blueprints, no straight lines or foundations, only patterns born of instinct and repetition. The octopus builds without plan, yet creates stability through destruction, complexity through consumption. Its dens, multiplied across coasts and continents, turn even the ruins of human neglect into pockets of renewal. In these scattered underwater cities, half natural, half accidental, the line between life and architecture blurs, and the sea quietly reminds us that engineering is not always the domain of intention. Sometimes it is the consequence of living. In the cold, green twilight of the continental shelf, the seabed breathes and shifts as if alive. At first glance, the landscape appears barren, an undulating plain of mud and gravel punctuated by scattered shells and tufts of algae. But beneath this surface, an invisible metropolis hums with activity. The architects are lobsters, industrious crustaceans whose constant excavation reshapes the benthic world grain by grain. Their burrows, winding through the sediment like vascular networks, are not mere shelters. They are engines of biogeochemical transformation, mixing the ocean's chemistry with the geometry of life. As the camera descends closer, the first sign of their presence appears. Not the animals themselves, but the architecture they leave behind. The entrances are circular and reinforced, rimmed by mounds of excavated sand that glimmer faintly under the dappled light filtering through the surface above. Fine silt drifts outward from the holes like smoke from underwater chimneys. Each burrow marks the territory of a single lobster, a solitary engineer guarding a tunnel that can extend several body lengths below the sediment. From this fortified refuge, it emerges at dusk to hunt, to molt, or to repair the damage caused by tides and storms. And through these daily acts of maintenance, it transforms the sea floor into a living system of constant renewal. A lobster's burrow is not random digging. It is a carefully balanced structure, the product of both muscle and memory. Using its spiny walking legs and fan-shaped tail, the lobster scoops, lifts, and pushes sediment outward. The claws, usually weapons and tools for feeding, double as shovels when constructing or expanding the tunnel. Inside, the walls are compacted with strokes of the abdomen, each motion sealing loose particles to prevent collapse. Over time, the interior becomes smoother and more stable, sometimes lined with fragments of shell or small pebbles that act as reinforcement. The geometry varies by species and habitat. Shallow water lobsters in sandy bays favor simple tunnels with one or two exits, while deep-dwelling species carve complex branching systems extending several meters underground. These burrows do not just provide protection from predators like cod, monkfish, and octopus. They mediate the movement of water, oxygen, and nutrients through the seabed. The process, known as bioturbation, is one of the least visible yet most important forces in marine ecology. As lobsters dig and maintain their burrows, they churn sediment continuously, aerating compacted layers that would otherwise become anoxic. Oxygen from seawater penetrates deeper into the mud, fueling microbial communities that break down organic matter. In the process, nitrogen, phosphorus, and trace metals are released back into circulation, nourishing phytoplankton that form the foundation of marine food webs. What begins as a mechanical act of burrow maintenance becomes a chemical cascade that sustains entire ecosystems. At this scale, each lobster is not just an animal but a living backhoe, cycling the ocean's building materials through its own need for shelter. Time-lapse imagery reveals this cycle in action. After a storm, when strong waves flatten the sediment and collapse tunnels, lobsters begin reconstruction almost immediately. The footage shows the burrow mouths opening like valves, sediment clouds curling upward as displaced grains roll down gentle slopes. Within hours, new ridges form around the entrances, redirecting bottom currents in subtle ways. These ridges create zones of reduced turbulence, small eddies where juvenile fish and invertebrates can settle without being swept away. The effect is measurable. Around active lobster colonies, sediment resuspension drops by nearly half, and larval settlement rates increase. What appears to be mere housekeeping actually engineers a safer neighborhood for dozens of other species. The seasonal rhythm of the lobsters amplifies this effect. In temperate regions, when spring waters warm and daylight lengthens, entire populations migrate from deeper wintering grounds towards shallower coastal zones. Here they molt, a vulnerable but essential process in which they shed their rigid exoskeletons to grow. Molting sites often overlap with dense burrow networks, forming what researchers describe as molting fields. For several weeks, the seabed becomes a patchwork of half-completed burrows, discarded shells, and fine sediment disturbed by the collective digging of hundreds of individuals. As each lobster splits its shell along preformed seams, it emerges soft, translucent, and defenseless. For hours or even days, it must remain hidden in its burrow, while the new exoskeleton hardens through the reuptake of calcium from surrounding water and sediment. The very mud that it excavates for safety now provides the mineral foundation for its renewal. This molting ritual links physiology to geology. When thousands of lobsters molt simultaneously, the combined flux of calcium and trace elements they release alters the local chemistry of seawater. Studies in the Gulf of Maine and the North Sea have shown measurable increases in dissolved calcium and magnesium concentrations during peak molting periods. The abandoned exoskeletons themselves, slowly breaking down, contribute additional carbonates to the sediment, feeding the microbial processes first sparked by burrow construction. Over the course of a season, these interactions create a self-reinforcing loop between biology and chemistry, a pulse of mineral turnover that coincides with growth and reproduction. Inside the burrow, the lobster's life is defined by vigilance. Every entrance is both an exit and a potential breach. Predators learn to patrol these holes, waiting for a careless movement. To compensate, lobsters maintain multiple escape routes where substrate allows. At night they emerge cautiously, antennae probing the water for vibrations. The long, segmented feelers can detect motion and chemical gradients several meters away, providing an early warning system that rivals the sensitivity of the finest instruments. When foraging, the lobster uses its smaller pincers, the crusher and the cutter, in delicate coordination. The larger blunt claw cracks shells and crushes prey, while the smaller serrated one slices soft tissue. This asymmetry is not fixed. Young lobsters can switch dominant claws depending on use, a rare example of morphological plasticity in crustaceans. Each lobster's burrow thus becomes both home and archive, a record of the individual's life and the environmental conditions surrounding it. Layers of sediment inside the tunnel can reveal years of ecological history, changes in particle composition, traces of storm deposits, and even variations in metal concentrations that correspond to seasonal runoff from land. In this way, the lobster's engineering writes a geological diary of the ecosystem itself. When marine geologists take sediment cores from old burrow fields, they find stratified evidence of repeated occupation. Zones of oxidized sediment alternating with darker anoxic layers, a fingerprint of life mixing the seafloor over time. The cumulative effect of these behaviors becomes visible only when viewed at scale. Across thousands of square kilometers, lobster burrow systems form patchworks of microhabitats that collectively influence coastal hydrodynamics. Water flowing across an undisturbed plain moves uniformly, carrying fine sediment in suspension. But across an area riddled with burrows, the flow becomes turbulent, broken into countless vortices that trap and deposit particles unevenly. This patchiness increases habitat complexity, which in turn supports more diverse communities of worms, clams, and small crustaceans. Juvenile lobsters often settle in the lee of older burrows, taking advantage of reduced currents until they grow large enough to excavate their own. Thus, the architecture perpetuates itself, generation after generation of engineers building upon the ruins of their predecessors. Lobsters' role as sediment churners also has implications for carbon storage. By mixing oxygen into deeper layers, they enhance the oxidation of organic matter that would otherwise remain buried. While this reduces long-term carbon sequestration, it simultaneously accelerates nutrient recycling, fueling primary productivity in nearby kelp forests and seagrass meadows. In essence, lobsters act as mediators of the carbon cycle, balancing the ocean's slow geological clock with the faster metabolism of life. Yet this balance is delicate. Human activity increasingly disrupts it. Bottom trawling can flatten burrow fields in a single pass, destroying years of accumulated architecture. Pollution and warming alter the chemical gradients that guide molting and mineral uptake. In some regions, heavy fishing pressure removes the largest individuals, the most efficient diggers and nutrient mixers, from the ecosystem. The loss is not only biological but geological. Fewer burrows mean less sediment turnover, fewer microhabitats, and diminished chemical exchange between water and seabed. The seafloor grows quieter, its once living texture replaced by static silt. Still, in untouched areas, the rhythm endures. As the tide recedes and light fades from the shallows, the burrow mouths come alive once more. Antennae appear first, waving cautiously in the current. Then, with a burst of motion, a lobster emerges, claws spread, body poised against the gentle drag of the water. It pauses, sensing the vibrations of distant waves, before setting to work. Sediment lifts in graceful plumes, curling outward like smoke from an unseen furnace. Every scoop, every flick of the tail, renews the landscape. In this quiet, unseen labor, the lobster continues a task that has persisted for millions of years, turning stone to life, mixing chemistry and architecture into one seamless act of survival. What remains by dawn is not chaos but design, channels smoothed by passing currents, eddies sheltering the young, minerals suspended and released to the sea. The ocean breathes through these small architects, its chemistry rewritten each night by claws and instinct. And though they move unseen beneath the waves, the lobster's work reaches far beyond their burrows, shaping coasts, feeding ecosystems, and binding the living and mineral worlds together at the scale of a single meter and over the span of an ocean's eternity. On the wind-scoured coasts of Antarctica, where the horizon is a study in white and blue, life begins in a riot of sound. Thousands of penguins gather on the black volcanic rock, their calls rising in a layered cacophony that cuts through the roar of surf and wind. From a distance, a colony resembles a mass of restless pebbles, but up close, it is a living machine of motion, heat, and nutrient exchange. Beneath their webbed feet, the dark rock is stained pink and green, evidence of their unending labor. Here, in a landscape too harsh for trees or soil, the penguin colony has become a biological factory. Every fish consumed at sea, every krill plucked from the depths, returns to land as guano, dense, mineral-rich waste that seeps into the earth and, in time, returns to the ocean. It is not just waste, it is currency. The penguins are, quite literally, feeding the sea. The guano forms thick crusts that crack underfoot, releasing the sharp ammonia scent that defines every rookery. What begins as a byproduct of survival becomes an ecological force, linking land and ocean in a feedback loop of staggering scale. Each breeding season, hundreds of thousands of penguins haul nutrients ashore in their bodies, nitrogen, phosphorus, and iron mined from the ocean's food web. They deposit it in concentrated form, often exceeding the density of a tropical rainforest's fertilizer output. When rain or meltwater runs through the colony, it dissolves and carries these compounds back into the sea, forming invisible plumes that drift outward along the coastline. Within days, the chemistry of the nearshore ocean changes. Microscopic algae bloom in the wake of the colony's presence, coloring the water with faint shades of green. To the untrained eye, it is unremarkable. To oceanographers, it is a signal of abundance, a flare of productivity sparked by the guano of millions. Satellite imagery now makes these nutrient fireworks visible from space. Instruments that detect subtle shifts in ocean color reveal streaks of chlorophyll-rich water, fanning outward from penguin rookeries for tens of kilometers. The pattern is seasonal, rising sharply after the breeding period when adults and fledglings leave the colony. These plumes, ephemeral yet immense, ignite local food chains. Phytoplankton, the microscopic plants of the sea, proliferate first, feeding on the influx of nitrogen and iron. In turn, krill swarm to graze on the bloom, followed by small fish that track the krill's movements. Seabirds, seals, and even whales capitalize on this pulse of life. The cycle becomes a rhythm, penguins feeding the plankton that feed the krill that feed the penguins again. It is an elegant example of biogeochemical reciprocity, land birds fertilizing the ocean that sustains them. Few species embody this reciprocity as powerfully as penguins. Unlike albatrosses or petrels, which scatter their nutrients widely across the open ocean, penguins concentrate them in tight, predictable zones. Their colonies are stationary, rooted in physical geography, rocky headlands, gravel terraces, or raised beaches close to the continental shelf. This spatial consistency turns them into nutrient hotspots, their ecological footprint expanding with every breeding season. Over decades, guano accumulates in layers several meters deep, forming a paleographic record of ocean productivity. Chemical analysis of these deposits allows scientists to reconstruct the history of the Antarctic food web, how krill abundance, fish populations, and sea ice extent have fluctuated over centuries. In recent years, genetic tools have made it possible to trace these nutrient loops in unprecedented detail. Environmental DNA, or eDNA, collected from meltwater near colonies, reveals the invisible fingerprint of entire ecosystems. From a single sample, scientists can identify the genetic traces of krill, fish, algae, and even bacteria living in the guano-enriched plume. This approach shows how penguin colonies amplify microbial diversity, acting as nutrient reactors that fuel microbial metabolism across the coastal zone. The bacteria that thrive here accelerate the decomposition of organic matter, releasing more bioavailable nitrogen back into circulation. Thus, the effect of a colony extends far beyond its visible boundary. It seeps into the chemistry of the sea, influencing productivity kilometers offshore. The process is most dramatic during the Antarctic summer, when sunlight returns and temperatures briefly rise above freezing. Meltwater streams flow through the rookeries, flushing dissolved nutrients into tide pools and fjords. The water turns turbid with suspended particles, each droplet carrying a microscopic payload of nitrogen and phosphorus. By the time this water reaches the ocean, it has transformed into a liquid fertilizer. In aerial imagery, one can trace the path of this nutrient surge, thin green tendrils of plankton blooming against the steel-grey sea. These are the living fingerprints of penguins, visible long after the birds themselves have departed for the winter pack ice. The connection between penguins and phytoplankton is not just chemical, but temporal. Penguins synchronize their breeding cycles with the productivity of the ocean. As the phytoplankton bloom peaks in early summer, krill and small fish follow, feeding in the nutrient-rich water. The penguins, in turn, time their chick rearing to coincide with this seasonal pulse, ensuring that their young hatch when food is most abundant. The system operates like a biological clockwork, energy flowing from the microscopic to the macroscopic with astonishing precision. But this synchrony also makes the system vulnerable. A shift in sea ice cover or ocean temperature can alter the timing of phytoplankton blooms, breaking the chain of supply that links plankton, krill, fish, and penguin. Ecologists studying this feedback loop refer to penguins as trophic connectors. Their existence bridges the gap between land and sea, surface and depth. When they feed offshore, penguins dive as deep as 200 meters, hunting fish and crustaceans that live in the twilight zone. Each dive draws energy from one layer of the ecosystem and returns it to another. The nutrients they digest at depth are redeposited on land, recycled by weather, and eventually carried back into surface waters. In this way, penguins act as living pumps, moving essential elements through different realms of the biosphere. This movement mirrors processes found in other systems: salmon transferring nutrients from ocean to river, seabirds enriching tropical islands. But in Antarctica, it unfolds on a planetary scale. The guano itself is a complex substance, far more than waste. Rich in ammonia, uric acid, and trace metals, it behaves as both fertilizer and mineral deposit. In the presence of oxygen, bacteria convert ammonia to nitrates, fueling algal blooms. Under low oxygen conditions, however, anaerobic microbes reduce these compounds, releasing nitrous oxide, a potent greenhouse gas. Thus, penguin colonies are both drivers of productivity and sources of emissions, their ecological influence spanning from local food webs to global climate dynamics. Recent research estimates that penguin guano contributes measurable quantities of nitrous oxide to the Antarctic atmosphere, a reminder that even natural processes carry side effects in the intricate chemistry of life. Predators play a subtler role in this cycle. Skua and giant petrels patrol the colony margins, feeding on eggs and chicks. Their scavenging disperses guano beyond the rookery, spreading nutrients farther inland and into the surrounding tundra. Over time, mosses and lichens colonize these enriched soils, forming rare patches of green in an otherwise barren landscape. These terrestrial oases harbor microarthropods, nematodes, and bacteria that depend entirely on penguin-derived nutrients. In this way, the colony's reach extends vertically, from the microscopic algae blooming in seawater to the moss cushions thriving meters above it. The dynamic extends into human observation as well. From space, satellites track the guano stains as reliable indicators of penguin population size. In remote regions where direct counting is impossible, the pink and brown patches visible from orbit serve as a proxy for colony health. Coupled with drone imagery and automated acoustic sensors, these data provide a near-continuous record of how penguin colonies expand, shrink, and shift with changing sea ice conditions. The same technology that tracks industrial pollution now reveals nature's own nutrient industry operating at the edge of the world. By connecting the dots, guano to plankton, plankton to krill, krill to fish, the story of penguins becomes one of elemental engineering. They are not just consumers at the end of a food chain, but initiators of one. Their colonies act as nutrient pumps, their migration patterns as conveyor belts of fertility. Through every feeding trip and every return to land, they bind two worlds that would otherwise remain separate. On the Antarctic coastline, life moves in circles. Nitrogen from the sea becomes guano on the rock, guano becomes bloom in the sea, and bloom becomes fish in the penguin's belly. It is an elegant economy of exchange, repeated endlessly in rhythm with the planet's seasons. As winter closes in and the colonies empty, the evidence of their influence lingers. The rock cools, the guano dries, and the wind scours away the last feathers and shells. Offshore, the bloom fades, and the ocean resumes its grey monotone. But even in this dormancy, the system waits. Beneath the ice, iron and nitrogen remain in circulation, ready to spark the next season's renewal. The penguins will return as they always do, driven by instinct and by the very productivity their presence sustains. And when they do, the nutrient fireworks will begin again. Tiny explosions of life cascading from rock to sea, proof that in the most remote corner of the planet, The link between land and ocean still thrives through the labor of a bird that cannot fly, but can reshape the chemistry of an entire sea.